I think I did 2 rows. Yeah, but still.
All right, let's take a seat. We got some work to do. So a few things before we continue with our quotient rule derivative shortcut today. The end of the quarter is on Friday. So Friday is your last opportunity to take the pass-fail. Just a reminder that that grade can affect your grade up to 5%. So if you haven't passed it yet, you can improve your score up to 5% because it's already a 0 in there if you haven't passed it yet. So the only way, your grade can only go up from there, okay, as long as you pass it. So Friday is your last chance. The other thing for tonight, I know I've been hitting you hard with these video assignments lately, and I apologize for that. There is another one tonight, but I'm anticipating it's the last one for this unit, okay? I think these shortcut rules kind of lend themselves well because you can get the phrase needed outside of class, and then we practice it in here, okay? But for the rest of the unit, I think we're going to do a lot of things together. So for tonight, I want you to check out 161 to 162. I think it's about 15 or 16 minutes-ish in there. Okay? Also, do me a favor and try to find an open or a blank page somewhere in your notes or a scratched piece of paper if you have that. I want to make sure that you have a go-to list of all these derivative shortcuts that we've been talking about because we have quite a few more to go over in this unit. So up to this point in time, we've talked about power rule, product rule, quotient rule, and then all 6 trig derivative shortcuts. We do have a few more to cover. If you take a look at the bottom page of my list, we'll be getting to all of these later in this unit. Okay, so we're kind of halfway there. So can someone refresh our memory on how the power rule operates? That derivative shortcut, the very first one that we went over? Yeah?
That would equal nx to the n minus 1.
There you go. You drop the power, multiply by the coefficient, and then the new power is 1 less. Looks good. What about our product rule shortcut? If we're multiplying 2 things together, how can we find our derivative? Goodney?
F of x times g prime of x plus f prime of x times g prime or g of x.
I think you said the same thing twice, so that's why I'm...
F of x times, or no, f prime of x times g of x.
There we go. Okay, so maybe some of you are familiar with the little phrase, if that helps you out. Do we remember that for product rule? Yeah? 1d2 plus 2d1. Good. All right. Now, over the weekend, I asked you to view the quotient rule. Can we write down what that derivative shortcut would look like, or the phrase, if that helps you? Go ahead, Kyle.
G of x
Uh-huh.
times f prime of x minus f of x times g prime of x, all divided by g of x squared.
All right. Does someone remember the phrase for quotient rule? Kind of catchy. Square the bottom and away we go. That's the second half. I've heard square the bottom and away we go, square the bottom and we're good to go, whatever that way. Go ahead, Melissa.
Low d high minus high d low.
Square the bottom and we're good to go, or away we go, something like that. All right, whenever I say that, it kind of reminds me of Snow White and the Seven Dwarfs. Like hi-ho, you know, but it's low d high minus high d low, okay? So I'll write it down. Low d high minus high d low, square the bottom, and we're good to go. All right, now also over the weekend, in relation to this quotient rule, we were able to find the other 4 trig derivative shortcuts because we can rewrite those trig functions as fractions. Before we tackle those, though, what's our derivative for sine? Yeah? Cosine. All right, and then derivative of cosine? Yeah? Negative sine. All right. What about the other 4? If you have to look, that's completely okay. Derivative of tangent. Yeah?
Secant squared.
Secant squared. All right. What about cosecant? Yeah?
Isn't it like cosecant times cosine?
Cosecant,
Times cosine?
cotangent,
Oh,
and it's negative. Okay. Instead of having to write cosecant as a fraction and then go through the quotient rule process, if we can remember this, it's going to be a lot quicker. So I'm not saying that this is the only way we get the derivative. If you have to produce it or derive it, you can. Okay, but if we can just remember this, it'll make our lives and problems go a lot quicker. Not our lives a lot quicker. Our lives easier and make our problems go a lot quicker. Okay? What about secant? If this made my life go a lot faster, I wouldn't be doing it right now. Yeah. Tangent times secant, okay? And then cotangent. Yeah?
negative cosecant squared?
Negative cosecant squared. Okay, now I know some of you in the Google form responses wanted some more practice with these trig shortcuts, and we'll get there eventually. But I wanted to take the time to just jot down some patterns that might help you remember some of these. And these are just things that students have told me in the past that helped them remember them. Maybe you can find your own patterns to help you, but I'll share some that have worked in the past. Okay, so one pattern that has seemed to help in some capacity is if you take a look at all of the C trig functions, their derivatives are negative. So there's a little clue. Another pattern that has helped students in the past, it seems to be that tangent and secant are related to each other. Okay, notice how they're related to each other here and here. You also have secant and cotangent related to each other in some capacity. So not sure if that helps you. Again, you have to do what works for you. However you can remember these shortcuts, that's all that really matters to me. Unless you want to do them the long way, because that's okay too. The next one, or the next kind of shortcut or pattern, I guess, I think was very creative, maybe a stretch, but for some reason it stuck. It was for this one specifically. So I had a student tell me once that he remembered this specific one because he thought of how if he spent too much time in the sun, he got a good tan. Can you see it? If you spend too much time, like seconds, SEC. If you spend too much time in the sun, you get a good tan. I don't know if it's a stretch or if it helps. Okay, but that was another pattern. Are there any other ones that you guys see that might be beneficial? And if you do, just let me know. We can go over them. But those are some ones that students have told me in the past. Do we see any more? If not, that's okay. No? All right. Well, if you do think of something, let me know. Okay, so I want this to be our go-to kind of list for derivative shortcuts, and we'll just keep adding to the list as this unit goes on. Okay, but this will be a good go-to piece of paper. In the meantime, let's take a look at page 153, and we're going to practice our quotient rule for today. So we're going to go through a bunch of examples of like low D high, high D low, square the bottom, and away we go. If you take a look at the first one, it's a fraction, so we definitely have the numerator, denominator, high and low pieces, which means we can go through our quotient rule to help us find the derivative. Yes?
I don't have page 53.
You don't have that one either, didn't you? You didn't have the other page before, right?
Yeah.
I don't know if I have an extra copy. I might. Tyler, I'm sorry I don't. Can you take them on a separate sheet of paper? Is that okay? Got it? Okay.
So 2 pages home.
All right, let's go ahead and go through our low D high minus high D low process. So our low function would be x plus 2, and then we got to multiply by D high. Can we write the derivative of the high function, or the top one? Go ahead, Kyle.
2x minus 2.
2x minus 2. All right, so low D high minus high, and then we need D low. So the derivative of the bottom would be 1. Square the bottom, and we're good to go, or away we go. So this is what the initial quotient rule gives us, but we're definitely going to have to practice simplifying it or cleaning it up, because I'm going to tell you right now, this is not what one of the solutions would look like on a multiple choice question. Okay, they're going to make you simplify it in some way. So we can definitely multiply these parenthesis pairs together, subtract them, maybe combine some like terms. We'll see what happens. So we'll have 2x squared minus 2x plus 4x minus 4. If we subtract the next quantity, the signs would change. And that's all over the bottom square. So if we combine some like terms, looks like we get x squared plus 4x minus 4 all over x plus 2 squared. I don't think we can factor the top, right? Two numbers that multiply to -4 but add to +4. No. All right, so I think we're good to go there. There's our simplified form. Okay. So the rest of these problems are just going through that quotient rule process and practicing the simplification to see what we can get. Let's try the next one. All right, so it's a fraction. We're going to go through quotient rule. We have low and then D high, the derivative of tangent. Yeah? Secant squared. Too much time in the sun. All right, so low D high minus high. D low would be 1. Square the bottom and we're good to go. So really, I think the only way we can simplify this one is if we were to distribute the secant squared in. So x secant squared plus 2 secant squared, and then minus the tangent all over the bottom. I know it looks like a lot, but that's technically our simplified form. Let's go ahead and try another trig one. If you don't like the thetas, you can make them x's. Okay, you just make the variable whatever you're comfortable with. All right, it's a fraction. So quotient rule, we need low times d high. Derivative of sine would be cosine minus high, and then we need d low. So the derivative of 1 is 0, nothing. Then we have to subtract the derivative of cosine, which would be go ahead, Tyler. You're saying it. It would end up being sine. Okay, so the derivative of cosine is negative sine, but if you're subtracting it, it would change to a positive. So we'll get positive sine. Good. So low d high minus high d low, square the bottom, and we're good to go. Let's simplify it. So if we distribute in the cosine, we'll have cosine minus cosine squared. The two sines would change into sine squared. And we have the bottom. Is that our most simplified form? Do you see anything in there that we could possibly do? What do you think, Tyler?
With negative cosine minus sine, or negative cosine squared minus sine squared.
It would be -1. Good. So if we think about that identity, cosine squared plus sine squared, that's usually 1. But notice how we have the opposite of that happening here, negative cosine squared minus sine squared. So this can actually change to -1. So we're left with cosine minus 1 up top, and we have a 1 minus cosine quantity squared on the bottom. I like that simplification. Can we keep going? What do you think?
You can rewrite the top as negative parenthesis 1 minus cosine, and then the bottom stays the same.
There we go. All right, so we can factor out a negative from the top, and notice how by doing so, it would match the denominator perfectly, so we could cancel out a set. So it looks like we have a -1 up top, and then the 1 minus cosine on the bottom. So since we're working with trig, that main identity might pop up sometimes. Cosine squared plus sine squared is 1. Sometimes you might have the opposite of it, though, if they're negative. All right. Let's try the next one. So if you take a look at the next fraction, we definitely are going to have to do the quotient rule, but we have a fraction within a fraction. So maybe we have to do the quotient rule twice? Maybe not. Can we rewrite the original problem so we don't have to do the quotient rule twice? So we don't have a fraction within a fraction? Yeah.
B minus x to the negative first over x plus.
I like that. Okay, so if you want to bring up that x, make it a negative power, that'll get rid of the fraction. You could do quotient rule within quotient rule, okay, but that might take some time. Still possible, though. Let's see what our derivative would look like. So we need low d high. So the derivative of 3 is 0. And then the derivative of the next term would be x to the negative second. So low d high minus high d low, square the bottom, and we're good to go. Now hopefully you guys can write a little smaller than I am, but I gotta kind of stack them. So if we clean it up, we can distribute in the x to the negative second. So we got to add the powers when necessary. This would be x to the negative first plus 5x to the negative second. And then the next parenthesis set, we can simply distribute in the minus. So that'll change the signs. let's see, combining like terms, we'll get 2x to the negative first plus 5x to the negative second minus 3 all over x plus 5 squared. We'll leave it like that. If you wanted to, you could move the x to the bottom of its own fraction, okay, not to the bottom of this overall fraction. It would kind of look like the original function a little bit. You'd have a fraction in a fraction, but we'll leave it. Are we doing okay? Low d high minus high d low, square the bottom, and we're good to go. All right, let's try the next one. Show, using the quotient rule, that if our original function is this fraction, then the derivative is this. So they're basically telling us what the derivative should be. We want to be able to prove that we can get there using appropriate derivative shortcuts, simplification rules, things like that. So the original function is a fraction. If we apply the quotient rule, let's see where we can go. Yes? Never mind? Okay. Let's do low and then d high. So the derivative of the top would be 2x plus 3. Yes?
Okay, I guessed that. This is where my question is. Couldn't you just factor the top and get x plus 1 and x plus 2 and factor the bottom and get x plus 1 and x minus 1 and then simplify it right off the bat?
That's what I was going to lead into. Yep. Would you prefer to do that? We'll get there. Okay? But see, Tyler, not everyone might see that. Okay? But that is awesome that you saw it. All right. Anyway, if you looked at this original equation and thought, oh, it's a fraction, I need to do quotient rule, you're probably going to do low d high minus high d low because that's your first thought process. But let's see what that leads to. If we do low d high minus high d low, square the bottom, and we're good to go, that's what the initial derivative shortcut leads us into. We need to simplify it to show that we get this. So we have a bunch of distributions to do, perhaps. So let's see what happens if we multiply these two together. We'll get 2x cubed plus 3x squared minus 2x minus 3. And then, if we simplify the other set, we got to distribute in a negative, but also a 2x. We'll get negative 2x cubed minus 6x squared minus 4x. And this is all over the bottom squared. Let's see, it looks like 2x cubes will cancel. So combining like terms, negative 3x squared minus 6x minus 3. What do you want to do next? We know what our final result should be. We just want to show that we can get there. So we still have a little bit more to do. Where do you see Hannah? How about a negative 3? Is that okay?
Yeah, that's what I meant.
Okay, so negative 3 from the top. All the signs would change. Can we keep going? It's starting to take shape. We have a negative 3 out front like we have here. That looks good. Can we keep going? What do you see, Tyler?
You can take the bottom and have x squared plus 1 and x squared minus 1, and you can take that even more and just go x plus 1 x minus 1 x plus 1 x minus 1.
Okay, so this would be x squared minus 1 twice. Okay, and those are both difference of squares. So this would be x plus 1, x minus 1, and same here. So we'd have x plus 1 squared and x minus 1 squared. I like that.
Then the top is x plus 1.
X plus 1 squared. Okay, so if we factor the top, bunch of factoring went on there. So plus 1 squared would go away, and we have negative 3 over x minus 1 squared, which is what we wanted in the end. Okay, so simplification process, even though the derivative isn't difficult, low d high minus high d low, square the bottom and away we go, it's the algebra or the simplification that might trip us up. So it's not the calculus, it's the algebra. And that's what we got to get used to or practice this year. Okay, the calculus is going to be pretty simple. It's the algebra or solving that can get a little difficult. So this is leading us into something else. Tyler, what did you notice? Instead of going through all of that.
You can just factor the top to x plus 1, x plus 2, and the bottom to x plus 1, x minus 1, and then cancel out x plus 1.
Let's see that. So instead of factoring after we did the derivative to get things to cancel out, what if we factored the original equation before we even find the derivative? So Tyler said the top factors is x plus 1, x plus 2. Bottom factors, x plus 1, x minus 1. X plus 1's cancel. So we have x plus 2 over x minus 1. So if this is what the original simplifies to, let's see if we can find the derivative of that remaining function. So it's still a fraction. We have low d high, which would be 1, minus high d low, which would still be 1, all over the bottom squared. So if we simplify it, did I miss something?
You can cancel the x negative 1.
So this would be x minus 1 minus x minus 2. And what was going to happen?
You can cancel out the x minus 1 factors on the top and the 1 from the bottom.
You mean like this? Cancel, cancel?
Yeah.
Not quite, because you're subtracting. If it was this times this, you could.
Okay.
Okay, but if you're adding or subtracting, you can't cancel individual terms. What is going to happen though is the x's will go away because one's positive, one's negative. And notice how you're left with negative 3 over x minus 1 squared. So what might be useful, okay, kind of a lesson, if you will, to be learned from this, instead of doing the simplification after you find the derivative, maybe if we do it before, it'll make the derivative process simpler. Do you see that? Instead of going through all of this, okay, we just went through 2 or 3 little things here. Okay, so if you prefer that, a little lesson to be learned is to simplify before finding the derivative. Okay. To simplify, to rewrite it, make it something simple for you to actually use a derivative shortcut for. I'm just trying to make your life a little easier. Okay, less algebra, less simplification. Try to do it before you find the derivative. All right, so what we're going to do is still talk about the quotient rule, but see how it can apply to graphs or tables. Instead of working with actual equations like we have been doing, how can we still relate these derivative shortcuts to different pieces of information? So on page 155, we have 2 graphs, and I think these are actually the same graphs from our product rule section. But we have 2 functions at the top that are listed as fractions. So we have p of x and r of x. When you take a look at the questions that they're asking us to do, okay, derivative of p and derivative of r, we're going to have to eventually use the quotient rule since we're working with fractions in our function. So let's try to find p prime of 5. If we find the derivative first, we're then going to plug in 5 to see what the value might be. So our p function is at the top, f of x over g of x. If we applied the quotient rule process, we'll have low, which is g of x. D high would be f prime, minus high d low, and then we got to square the bottom. Low d high minus high d low, square the bottom, and away we go. So if this is our derivative using our quotient rule shortcut, let's plug in 5 to see what our slope value would be. So this is where the graphs are kind of going to help us out. What is g of 5? Can we find it? Is that 5? 1, 2, so like 5? Okay, so there's that value, and then we need f prime of 5. So the slope of the f graph at 5. So if you go to the f graph, plot the point, what does the slope of the graph look like to be at that spot? In other words, what's the slope of that line? Yeah? Close. You go down one, and negative a half. There you go. Down 1 over 2. All right, let's keep plugging our information in. So f of 5, the point looks like negative 3.5. And then g prime of 5. So what's the slope of the g graph at 5? 1. Good. All over g of 5 squared, and I think we said g of 5 was 5. Okay. So we applied the quotient rule shortcut, but now we're just using the graphs to fill in the different pieces. Let's go ahead and solve. So 5 times negative a half is negative 2.5, then plus 3.5 over 25. So we're left with 1 over 25. There's our slope. That's really shallow, isn't it? You go up 1 over 25. It's a really shallow slope. All right, let's try r prime. So the r function is a fraction at the top. We're going to go through our quotient rule shortcut. So we have low, and then d high, the derivative of sine. We got cosine. So low d high minus high d low, square the bottom, and we're good to go. Let's plug in 0 and see what happens. So f of 0 looks like negative 5. Cosine of 0 on our unit circle, the very first point, yeah? 1, okay. Minus sine of 0, sine of the very first point. That's also 0. And then it wants f prime of 0. So on the f graph, if you went to 0, drew in your tangent line, what does that slope look like? Can we estimate it? Yeah?
Like 2.
Probably 2. Notice how it really doesn't matter though, right? Because you're multiplying by 0. But at least it's a good recognition. Okay? And then f of 0 we said was negative 5, and we're going to square that. So in the end, we have negative 5 over 25, or negative 1/5. All right, let's see if we can take these results a little further, because they're going to ask us for the bottom 2 questions, the equation of a tangent line. What do we need to know? Yeah? Point and a slope. Okay, so they're asking for the equation of the tangent line for P at 5. So we've got to figure out P of 5, but also P prime of 5, which we already found, right? At the top. That was 1/25. So let's see if we can figure out our point. The P function was the F graph divided by the G graph. So if you were to plug in 5 into both graphs, and then take the F answer divided by the G answer, what would we get? let's see, if you plugged in 5 into the F graph, we got negative 3.5. And if you plug in 5 into the G graph, we got 5. Can we figure out what negative 3.5 divided by 5 is? Can we write 3.5 as a fraction? Yeah?
Negative 7/2.
7 over 2. Okay, and if you divide that fraction by 5, meaning multiply by the reciprocal, we get negative 7/10. Alright, so point slope, we know it. We'll do y minus the point equals the slope times x minus 5 in this case. Alright, let's try the same thing for r of x. So we still need a point and a slope. So we got to figure out r of 0, but also r prime of 0, which we conveniently already have. So the r function was sine divided by f. So sine of 0 is 0 divided by f of 0, which was negative 5 from the graph. So it looks like our point location is 0. So y minus the point equals our slope times x minus 0. Are we getting better with point slope? Slowly? Okay. How are we doing with graphs? Okay, iffy? Still getting there? Day by day. Alright, let's check out a table on the back. We might be able to get through one of them at least. Okay, let's check out let's do this one actually. We'll skip the first one. If p of x equals g divided by f, what's the value of the derivative at 4? And then what does that actually tell us about the f function? So we have to figure out something, but then analyze what that answer means. So let's check out the derivative first. Our function is a fraction, so we're going to go through our quotient rule process. We have low d high minus high d low, square the bottom, and we're good to go. Let's plug in 4. So f of 4 from the table was 1. G prime was negative 2. Regular G was 7. F prime was 8. Let's see, all over the bottom, f of 4 was 1, and we gotta square it. So negative 2 minus 56. Negative 58. So there's our slope value. What does that say about the graph of p of x at this spot of 4? Can we interpret it? What do you think, Tyler?
It goes up 58 and
Say it again.
it goes up 58 over 1.
Over 1. Oh.
Or down 58, sorry.
It goes down 58 over 1. So it's a very steep negative slope. So if it's a steep negative slope, how is your graph behaving? If you go here and you go down 58 and over 1, so your graph is decreasing, right? Isn't the derivative negative? That's our connection. Okay, so we'll say p of x is decreasing because p prime is negative. So specifically at this spot of 4, the graph is decreasing. It might be increasing at other spots, but we'd have to analyze those. All right, we'll try the other 4 tomorrow, and then we'll pick up with our other derivative shortcut from tonight. Have a good night, guys.